Here is 106.
It's a pleasure to have Francisco Morales, who will give classes on instantons.
Okay. Okay, maybe I will start with. Okay, all the students are from PhD, and here more or less want to.
There are also some students coming from the end of the master thesis.
No, okay. I will try to assume that you don't have any background apart from quantum field theory. I need some supersymmetry, but I will review very few. You are already giving something, very something of supersymmetry from the other lectures, but I will review the part that I will use. And I will try always. If the subject is too long, try at least to give you an idea of what do you need on top of, but basically it's just quantum physics. Let me give the outline. There are 5 lectures. The first one is, I will introduce what is instantons. Definition, and why they are important, why they are relevant. Okay, why? Interesting. Let me anticipate the answer. Instantons are just solutions of the Euclidean sequential motion. And why they are interesting? Because they provide the leading contribution to amplitudes in field series. For example, in field series, you want to compute correlators, for example. So, correlators. And this in quantum mechanics or in quantum field series are always given by path integral. So giving operators. Okay. Typically, imagine you want to compute the scattering of gluons. You have 4 gluons, and you want to see what is how they scatter. This is related to the 4-point function. Therefore, you want to compute this integral. Okay, and we know that in the classical limit, that h is going to 0. You see, the basic contribution comes from the minimum of the action. It's equal to 0. Okay, therefore, instantons, as we will see, will be just the solutions of these equations. Okay? Why Euclidean we will come now in a few minutes. Okay? Then essentially, you can imagine this as a sum over all vacuum, or possible vacuum, means all solutions of this equation, of some coefficients. And then some, we will see that essentially what will happen is that for gauge series, what we will see that instanton are large by an integer, and essentially leads to suppressions, to contribution to the correlators, which are suppressed. You see, if G is small, this is exponentially suppressed. Okay? This is very small. Okay? Typically, you are used to the fact that you are in a trivial vacuum. You know, all quantum field theory you have seen with Feynman diagrams and so on. But in the trivial vacuum, K is equal to 0. For you don't have that. And here you have just the 1 loop, 2 loop, 3 loop, and so on. Okay. instantons are much smaller contribution for that. Then you say, why we care? We care because in QCD, the coupling constant is not small. Therefore, in electrodynamics, instantons are irrelevant, or in any gauge theory where the gauge coupling is small. But when the gauge coupling is strong, we should look to these effects. This effect becomes important. Therefore, if you want to ask questions like confinement or chiral symmetry breakings and so on, you should address the study of things. Therefore, this course will be giving the rules, the tools to study this type of corrections. 1, 2, 3 series. Okay? Okay, this is a sort of motivation of what this is. In this lecture, this first lecture, I will introduce, and we see that what are gauge instantons. Okay, then gauge instantons is very simple. If you solve this equation in a gauge theory, Euclidean action, the minimum of the action, we will see that the solution is very simple. You just say that the F should be self-dual or anti-self-dual. Therefore, in gauge theories, all this we will see very precisely. Instantons are simply self-dual connections. And just gauge field configurations such that if I take the dual, I will see the same. Okay? Then I will describe explicitly, I will write the K equal to 1 instanton. Solution. Okay. And that's all maybe for the first lecture. Then lecture 2, I will do what is called ADHM construction, which essentially is K bigger than. It's a construction of the most general instant for any instanton. This K, remember, is just say, we will see explicitly what this means. But just think of labeling the instanton configuration. How big is the action? Okay, then I will introduce Fermions. Okay. Instanton, I say you, is some connection, AN instanton, okay, such that the discrete is self-dual. What means Fermions? Fermions are solutions of the Dirac equation. But now this covariant derivative will be a covariant derivative with an A, the connection of instanton. For this lecture. This lecture is a bit technical. It could happen that I start today this part and I will end in lecture 3. I mean, this lecture is a bit longer than the other. Okay. Supersymmetric. Yes. Here I will start with a very quick review of the superfield formalism. Okay, what is a supersymmetric theory? Supersymmetric theory, okay, you already started this morning to learn about that. It's just a theory in which there is a symmetry that relates bosons and fermions. Okay? The theory, they have the same number of bosons and fermions, there is a symmetry. Everything, the theory is symmetric if you exchange the two. Okay? There are various types of supersymmetry. The minimal is n equal 1 supersymmetry. But you can have extended supersymmetry, n equal 2 or n equal 4. Of course, any theory can be written as an n equal 1. Any n equal 2 supersymmetric theory is also n equal 1. Therefore, I will always use this formula, the formula of the minimal supersymmetry. And I will just show you what is different in the case of n equal 2 and n equal 4. Okay? And in this first lecture, what I will do is do a simplest instanton computation of a superpotential in an edible box. This is called Affleck-Dine-Seiberg superpotential. This is the simplest example where an instanton generates a term effective function for use. Okay, this is this lecture, lecture 3. Lecture 4, I will do computations n equal to supersymmetric. Okay. Let me say that the superpotential, we will introduce all these terms. Okay, let's say superpotential is given in terms of a holomorphic function. This is what we will compute here. In n equal to, again, all the dynamics of the theory is described in terms of something which is called prepotential, which is again a holomorphic function. Okay? The main difference between these two cases is that for n equal 1, we see that only k equal to 1 instanton contribute. Why? For n equal to 2, any k. Okay? Therefore, you can imagine that this computation looks much difficult than the other. Here I should take into account all possible instanton contribution. But there is a technique which is very popular in these days, which is called localization. Can you imagine that for 20 years, people tried to compute k equal to 2 instant? And after 20 years, they know how to compute just k equal to 1, and in few cases, k equal to 2. This situation changed a few years ago, thanks to these techniques, localization, and now it's used almost everywhere. And with this technique, you can compute any number of instances. Okay? It's a very simple idea. I will explain it from first principles, and we will see, we will even compute some few terms for this calculation. Let's see. Lecture 5, I don't know if we will arrive to this point. In the sense that for me what is important is that you can follow me. For even if we arrive here, it's okay. But okay, I will try to say something about Seiberg-Witten. Which is a nice geometric structure behind this computation here. Essentially what we will see is that how using localization you can prove these techniques give the same answer. By the way, initially people compute this prepotential using these geometric techniques. It's not from first principle. They just realize that the theory has a lot of symmetries, and just from the symmetries you can write the curve that encode this holomorphic function. In the beginning, this is how they compute this curve. Now we can compute directly using this formula, and we can prove this Seiberg-Witten curve directly from a microscopic point of view. Okay, if I have time, I will say this. Please stop me at any time. Say me if I am going too fast or slow. Any question? And you also stop me when the time is finished, because I don't have the... Okay. Okay, then we will mainly deal with case series, although many of the things I will say are valid for all other quantum field series. Okay? Therefore, essentially, in a quantum field theory, the main object you want to compute are some correlators. Which are simply defined by the integral over all possible fields of the operators. And then you have this exponential. Yeah. Okay? Where the action, for example, for our case, this will be a gauge theory, is 4 g squared integral e for s f n n f n n a plus other stuff. Okay? This is the type of objects that we will study. So, here we go. Okay, where by mu, I always will use this. Okay, and this you raise and lower the index by this. This means that I mean by this 4g squared integral for s minus F0i. F0i. Okay. So, plus okay, now you already notice that this action is not positively defined. Okay, as usual, no? We are taking a term of the potential, we have different signs. Therefore, if I want to evaluate h goes to 0, then this, in order, I should try to define a path where this action is positively defined, such a way that I can do the standard saddle point approximation. And the simplest way is just notice that you can just go to the Euclidean. Okay? You essentially do an analytic continuation of t to minus I t Euclidean. Okay? What happened here? This is equal to minus 1 over 4g squared. Here you have now d for s. This was dt. dt becomes minus I dte, therefore this is t3x dte. Okay. Then let's compute is. So I have I squared here. Okay, and what is here? What appears here now is discrete design. Therefore I can write this as fmn. Therefore I get something, okay, this is plus 1. Therefore this is minus S Euclidean, I call this S Euclidean, which is something which is positive, definite. Okay, for this integral, I can write after analytic integration as integral of d phi and the crucial point is that now I have here something which is positively defined. Okay? This is positive, you see, it's a square of something. I use n index to say that this is a flat index. I can raise and lower this whole index, while mu is an inconstant. index. Okay? Then in the whole lecture from now on, I will just use MN index, just Euclidean. Okay? This is the Euclidean. And now it's very simple to compute this integral, because if now it ends h goes to 0, you see that this is exponentially suppressed. Unless the main contribution will come from the minimum of this action. If this is minimum, this is bigger. Okay? Therefore, this integral is dominated by the extreme, by the minimum of S. Okay? Therefore, I call an instanton definition. Instanton is the minimum of the Euclidean and then this integral will be a sum, these correlators, will be a sum over the minimum of something, some exponential to the minus evaluate at the minimum. Therefore, it's a sum over the instantons, the sum over the instantons of the Euclidean action evaluated at the files. Okay? Therefore, what we will do in this lecture is first find the minimum, construct a species, evaluate this action, evaluate this sum. Okay. Let me give you also another application of instanton which is irrelevant for what I will say here, but maybe you will listen in other contexts just to know it's the same thing. For example, if you have in quantum mechanics, for example, you have a particle moving into some potential. Imagine if you have a particle and you study the energies. Or the energy level of this particle. You see, if this barrier, imagine you have two barriers, you have two minima, okay? You're parting one minimum. If this barrier is very big, very high, this particle will not know anything about the existence of a different barrier. You expect here just the spectrum of the harmonic oscillator. Okay? What happens is that in quantum mechanics, we know that you should take the minimum over all possible. Therefore, this particle will always know that there is an opposite, because there is always a probability that this particle will come and jump here. Okay? Then what you see is that all these levels is split into the level of the harmonic oscillator is split into, and this distance delta is proportional to E to the minus S Euclidean, where S Euclidean simply measures the probability that the particle comes from here to here. Then you see the instanton measure how I split the levels in quantum mechanics. In other words, it just measures the tunneling effect between two values. So we will, here this will not be relevant because we will study case series, but just to keep in mind that instanton solution of the Euclidean equation points there in every context you can apply. For example, in this case, it's a nice application. You can compute. This is very nice. You just compute this transition. It's just the action. This will be just evaluate the action on a particle moving from here to here. You see that you get exactly this factor, this delta, the harmonic oscillators, the energies. You will find something like plus 1/2 plus minus 1/2 delta, the frequency. And this delta is exactly computed by the instanton. Okay? Therefore, think always of instanton as measurement of effects or a solution as minimum of the Euclidean. The important point there is Euclidean. Okay. Now we go to gauge space. Then the first thing that we should write is the equation. Let's define what is a gauge state of a free strain Okay, this was the F, sorry, I wrote here. A was, this is now in a group. This F you can imagine as a Fmn is some matrix. Okay, then in other words, all these quantities are matrices. For example, for SUN, I will always do SUN in these cups. Therefore, you can imagine this as matrix n by n. Then TA is a matrix n by n. You can do any group. Okay, let's just focus for completeness in one case. Therefore, F is given by this. And it would be also interesting to introduce this quantity, F tilde, which is just the dual of F. Okay, and let's first notice that this quantity satisfies an identity, which is called Bianchi identity, which is just dm of Fmn theta, which is just by definition, this covariant derivative means derivative m plus commutator Okay, let's notice that this is 0. Identically, for any field strength, the dm of Fm tilde is 0. It's computed. I just plug this here. Therefore, I have dm of, okay, I have here 1/2 epsilon m pq. Then here I have dm of fpq. Fpq is d p a q minus pq a p plus okay, this is dm of that plus commutator of an times d pq dp a q. Okay, let me do simple. This is antisymmetric, but there is also here antisymmetric. Therefore, I can factor 2. One in front, commutator, and you have also commutator an a p a q. Okay. Now you can see that all terms cancel. For example, look to this term, dn dp. This is symmetric with respect to exchange of the two derivatives. But here is antisymmetric with respect to that. Therefore, this term cancels. The same here. M and Q are symmetrical when they change. This is antisymmetric. It's cancelled. And you can go ahead. For example, you have here this dp dn, and you can see that this cancels with one. Then again, using the Supersymmetric. Then it's just everything cancelled, apart from this last one. And this cancelled by something which is called the Jacobi identity. I have seen that. Okay, it's good. Therefore, this cancels due to the Jacobi. And the other cancels just because the antisymmetric distance. Therefore, this is a very simple identity satisfied by the field strength, by the dual field strength, and this is called Bianchi identity. Let me write. It's called Bianchi identity. On the other hand, the equation of motion is this. You see, if I do the equation of motion here, I should take the variation with respect to A and put the derivative on top of F. Therefore, the equation of motion is simply this. This is field. Okay. Then could anyone see a solution for this equation? You see, there is a solution for this equation if I take Fn is equal to F tilde Nn. This is automatically the solution. And this is what is called gauges. Sorry, I still didn't show you that this is a minimum. Let's compute now the action and show that this is a minimum. Okay, but for sure, this is a solution of the question. Now let's see if it's a minimum. Okay. Where is the action? Action was here. Okay, let's first notice the following. See, we have P4x. This we all agree, no? This is a positive quantity, the square of a positive one. This is for sure bigger than C. Okay? Now let's compute this. Let's expand this. This is d4x trace of f squared plus trace of f tilde squared plus minus 2 trace of f. And we know that this is bigger than C. Now you can compute, you can see that trace of f tilde squared is equal to trace of f squared. Therefore, all this is simply 2. Therefore, I get from here that the integral of d4x trace of f squared, okay, is bigger or equal than this quantity here. No? With a plus or minus. Let's say the modulus of 2. Yes. Okay, now you see what we find. What we find is that any field configuration you compute the trace of f squared will be bigger than that, bigger or equal. But when f is equal to f dual, sorry, there is not 2 here. There was a 2 here and a 2 coming from here. Okay? Then we have every field configuration, this is bigger than that. And this is equal only if f is equal to f dual. You see, if f is equal to f dual, these two things are equal. Okay? Therefore, the instanton are the minimum for this one. Once you fix this one, that we will see that this is an integer, it's a number, topological number, that simply qualify all configuration with this given topological number. From all this configuration with this given topological number, the instanton is the minimum value of the Euclidean. Okay? Therefore, we see that the solution of the Gaussian function is the minimum for a given value of this. Now, are you familiar with the chain class? Who is familiar with chain class or topological? The fact that place of f which is a number. Okay, let's do. Okay, let me first state this and do in a simple example in which we can compute and see what is this. Okay. Okay, the statement is the following. If there is something which is called the sharing class of a string of a field of a connection, which is defined as the exponential I f over 2 pi. Okay? And it's such that any integral of f on a value on a any, of course, this should be to the n-dimensional surface. This will be an integer. This is the statement. Okay? It's a mathematical theorem that says that if you take a connection and compute this exponential, any integral of this is an integer. Okay? Sorry, I should first introduce what is f. There are two languages to f. Till now, I always work with coordinates, with components. You can write with forms and define f as 1/2 f and then yes. It's a two-form in the space. Okay? And for example, let me give you a few formulas. I mean, every formula I write here, I can translate in terms of forms. For example, integral of fmn for x 1/2 is the same as integral f. All these formulas you can compute. You see, I give you all the ingredients. You take this, take the wedge of that, and see that the coefficient is exactly fm.
Just maybe I'm wrong, but should there be a wedge between the x's in your?
Okay, d for x, in product I mean wedge.
Okay.
Let's say that when I work with forms and I write f squared, what I really mean is f. When you write with forms, the natural product is the wedge. It's good. It's a good point. This is really, you see, otherwise this will be 0. Because this is antisymmetric and this is, this is a good point. This is one formula. The other formula is integral d for x. fmn fn theta. Sorry. No, these is a multi-form. When you do the integral, only the form of the dimension domain will contribute. Okay. This integral means that you pick out of this, for example, if you're in 2 dimensions, it's just you pick the first term. If you're in 4 dimensions, you pick the 4th term.
But it's a finite series. But it's a finite series.
This is in principle, it's an infinite series if you are in a space of infinite dimension. I mean, it's a finite series. For a space of a given dimension, this is a series that extends at the dimension of the space. Okay, the nice thing, this is just a mathematical statement, is that you see that this object we are computing here is precisely FHF, which means that it's exactly the second Chern class. Therefore, it's a norm, it's an integer. Now, to see that this is I will now show you, for example, a simplest example of this, just to give you an idea how you can compute in general this type of, how you can understand this topological matrix, and what is the meaning of this topological matrix. Now, let's do just the dimension 2. So again, this part is irrelevant for what I will say. It's just because just you don't feel this too abstract. Let's compute the first one. I over 2 pi integral of f over R2. Okay? Imagine that you have U1 theory, U1 Gauss theory on R2. Okay? Then according to this theorem, this should be an integer. Okay, some integer. Let's see that this is the case. For example, what is f? So, I over 2 pi integral of f is I over 2 pi. F is dA. You see, f what is this? 1/2 dm xn, and fm was dm. Okay, I cancel it for. F is just d of a. Okay, but this is a total derivative for a time integrator. And write this as the integral of the boundary of R2, which is what is the boundary of R2? It's a circle. Circle infinity of A. Okay? Now, at infinity, you see, if this integral is finite, at infinity, f should be 0. Therefore, this A should be a total, a gauge, AN. It should be a pure gauge at infinity. Okay? For U1, you can just take, for example, U, you take, I don't know, e to the I theta, times k, let's say. So it should be a phase, no? If this is U1, U bar should be 0, should be 1, so this means that this should be some phase. Let me call AI theta k. It should be integer because theta to 2 pi should come back to the same pi. Therefore, what is that? This is, let me do the minus here. This is just minus I t theta times k. Okay, I plug here. And this is I over 2 pi integral between 0 and 2 pi of this minus I k d. Okay? This is minus I with I drift plus 1 over 2 pi k integral between 0 and 2 pi d theta t k. Therefore, you see that this integer k first is an integer, it's the first Chern class. Second, it measures how many times the gauge at infinity, this circle, which is in the gauge part of the group, wrap the sphere at infinity. Just one minute. For the x, it will be exactly this. You imagine the sphere at infinity is S3, you will have an SU2 gauge sphere, and you ask yourself how many times the instanton moment is k, which is the analog of this, but now with FHF. FHF will be again an integer, which measures how many times the S3 of gauge at infinity wrap the S3 in space.
What would happen if you integrate using a torus or something else, for instance, instead of a R2.
You can do the same. Yes, yes. This is valid for any surface.
But then what is the meaning of the K? I mean, there you have two cycles, so there's
exactly. This will not be. Sorry. You should integrate over two cycles. It also have only one two cycle.
okay, yeah, then take something else. Then.
If you have something bigger and integrate, then you will not. If the map, in this case, is an integer just because you have a sphere to a sphere.
Okay.
If you have a more complicated space, you should ask how many now go from one space to the other space. And this will say how many integers, for example, you could have for example, if you have various cycles, various two cycles, you will have various integers which precisely say how many times you have one cycle or the second cycle. But the crucial point is that, you see, what you're saying is correct. For every non-trivial cycle, you will have an integer. You have various two cycles, various 3 or 4, you will have various integers. Okay, it's clear? Therefore, we come back here. Now let's see what is the second term class here. This is 1 plus IF over 2 pi plus IF squared, this means minus F squared over 4 pi squared and 2. Okay, therefore this is an integer. Okay, therefore f tilde here we say that the Euclidean action is minus 1 over 4 g squared integral d4x fmn fmn. Okay? And we say that f is self-dual, therefore I can put a tilde. Okay? Let's do it instead. Then this is minus 1 over 2 g squared integral of f wedge f. Okay? But f wedge f, we learn from here that the integral of f wedge f is equal minus a b squared times an integer. Okay? So we come here and we say that this is minus, sorry, okay. This was like that. It's better to write with a trace. I write the factor of 2. I'm using these conventions. This is a matter of convention. Trace of TA TB is equal to 1/2 delta AB. Therefore, either you write 1/4 FMN AA, which means sum over all possible components, or 1/2 trace. We always write the trace explicitly. Okay, therefore we have this. Then this is inside the 2, no? Because we say that 1/2 FMA, FF tilde, 1/2 F tilde is just F wedge. Okay? And this is AP squared K over G squared.
What happened to the tilde? There's a tilde there. So it's FF tilde.
Ah, yes. We say that this is an instanton. Therefore, write the tilde or no, it doesn't matter because they are equal. But when you put the tilde, you can use, it's correct, it's better to write the tilde because you remember that this is equal to F wedge. Only for the instanton this is true, not for an arbitrary. Therefore, what we learn is that, you see, this was the factor we were talking about. If K is large, what we are saying that the correlators will be a sum over K of this factor e to the 2 pi square K over G squared, and here some numbers. Any correlator in quantum fields here will be a sum over K The first one, k equal to 0, is the one that we are used to use. It's just a vacuum in which f is equal to 0. This is also a minimum. F is equal to 0 is a minimum. This is the standard. This will give k equal to 0, no instant. After that, they will start with k equal to 1, will be the first non-trivial one, k equal to 2, k equal to 0. If GML is small, all this you can forget it. It's covered. If you are in QCD, then you should keep it. The main problem of understanding QCD is exactly that. That we don't know how to study strong coupling. Now we will see that we in these lectures, we will be able to compute also these strong coupling effects, but still for a theory which is a bit simpler than the real world, which are these supersymmetric series. This lecture cannot solve the problem still, because in QCD, unfortunately, still we don't have Fermions, we don't have supersymmetry. But at least it's a way to, it's a simple situation where we can compute the things, and we can see that there are some supersymmetric theory that confine, we can see confinement, we can see many of the features that you see in QCD, we can see in this supersymmetric theory, although they are not still what we need. Okay. Okay, questions? Then what we have seen till now is that instantons are minimum of the Euclidean equation motion, and the action is given by a simple topological numbers. And okay, and now what we will do is solve this equation.
So if you had taken the anti-subgroup solution,
The
anti-subgroup solution.
it's the same, sorry. In all this analysis, you see there was a modulus here.
Yeah.
I can take either Septuar or anti-Septuar. Okay? And here what will appear is just a modulus. Therefore, all what I am saying, you always have a tower of instantons and a tower of anti-instantons. Okay? Okay. Therefore, I will always, I don't know, in these lectures construct instantons, but imagine you can repeat the whole stuff for an infinite. Okay, now let's see the simplest instanton one can construct. What is the time? 50. And when it finish?
5.
5. Okay, good. Then let's construct the simplest one. Sorry, I don't know if how you organize, if you prefer a break, how it works here.
It depends on you.
If for me, it's the same. You can even make a break of 5 minutes if people want after 1 hour, or
You prefer for a break in the middle?
or with, to me, it's the same. You should just say how you are used to it.
It depends. Right now I'm fine, but maybe tomorrow I want to.
Okay, you let me know, because I don't know. But when you will find when you get tired. Sorry, have anyone an opinion on that? Okay, it's a nice exercise to repeat the exercise I did here for F, to F wedge F, and try to see that this again an integer. If somebody is interested in that, I can do some insights on that. Okay, let's do a k equal to 1. Okay, the main observation to constructing circular connections is that there is a very simple object that you can construct, which is set to one just out of the Dirac matrices. Let's introduce the Dirac matrix. Sigma m, I define as I tau 1, sigma bar n is minus I tau 1, and tau are the following matrices. Okay, these are the Dirac matrices. What you can check is that this object is the problem of this, is certain. Sorry, sometimes I put index up and down. This may not sense. I mean, it's flat index. I put up and down, it's the same thing. The metric here is always. Okay, this is for example, let's look one of them. For example, 1/4. 1/4, what is here? 1/4 of sigma 1. Sigma 1 is alpha 1. Sigma bar 4 is the identity, minus sigma 1, sorry, sigma 4, which is the identity, sigma bar is minus plus alpha 1, okay, and this is just I half 1. This is just sigma 1, 4. What is sigma 2, 3? Sigma 2, 3 is, I'm just doing explicit just to show you that I'm saying a triviality. 2 is I times minus I is plus 1. It's so trivial that I can. Okay, 2 and 3 is sigma 2 is tau 2 times tau 3, and I have I and minus I, which is plus 1, plus the other, you see that this again is tau 2 tau 3. So this is I over 2. And this is tau 2 times tau 3 is I tau 1. This is correct. Tau 2 times tau 3 is I this time this is 0, this time this is I, this is I, this is okay? Therefore, you see that sigma 1/4 is equal to sigma 2/3, which is this statement, because sigma 1/4 is equal epsilon 1/4 to 3 sigma 2/3. Okay? And 1/4 to 3 is 1 because you should do 1 and 2. Okay? Therefore, this is certain. You can compute all the other components. You see that this object is certain. Good. Then, how I construct a self-dual connection? I look for a fixed plane proportional to this. I just look to Fn, any function, times sigma n. Here, any function. Okay. This is for sure self-dual. Okay? Any function I write here is self-dual. Okay? Because sigma n is self-dual. But I should also see that this Fn is not enough. It not only should be self-dual, but also should be the Dn An this net plus An. Okay? In other words, I should find a connection. The way you do is you put any function here, and then you write a connection such that when I compute this, now I give the answer, and then we can verify. Now the claim is that if I compute now this derivative m plus commutator of am and n, I find this expression. Okay, then this is exercise. It's very simple. You should just take this, compute the derivative. So the derivative can hit here or can hit here. This will be two contributions. And then you can compute the commutator of this. Guys, this is sigma matrix times another matrix of the same type, commutators. You use properties of this sigma and find that this is given. Okay. But the important point is that is that you have constructed a field strain which is proportional to sigma mn and therefore is automatically an instant. Therefore, exercise showing that F associated to AM is star. This is one. Do the exercise because I think all this is very useful. You get familiar with all these forms.
So why did you pick that function?
Right.
No, I don't pick it. I say that in general this can be any function, but it's very hard to find a function which is you should find a function such that the derivative of that was this commutator, and this function makes this. If you start from this, you compute the field strength of that, and you see it's proportional. Essentially, how they did that? They start with answers. No, they want a sigma mn, which the vector what you can write. With the vector you start. Okay, it should be proportional sigma mn. Then the only vector they have is the position. This is the x, is the only thing that they have. Then you start from this, and then put here some function of x. Any function of x. Now compute derivative, and see fit this function in such a way that you get. This is how TÜV, it's called the TÜV solution. This was found by TÜV at the time. Of course, it's not trivial. This was a paper, a very famous paper. Just to find. Now it looks
it's also not unique, right?
Eh?
Is it unique? Is it unique?
It's already not unique. You see, you have this parameter. It's
well, up to the parameters.
I come now to this. It's unique. I will show you now what is the most general.
Okay.
I said that it's unique up to this x0 is a parameter, 4 parameters. Rho, then 5, plus SU2 rotation, because I can always multiply this by U and U dagger of SU2, 2 by 2 matrix of SU2. And this 5 plus 3, 8 parameters, this is the most general solution. Therefore, it's unique. It's not unique. There are infinite solutions, but that 8-dimensional modular space of solution.
Yeah, but I mean, after choosing that function, or can I choose a different?
You cannot find
right.
any self-dual solution which is apart from this one up to rotation of SU2. Just that.
Okay.
How can the field strength be gauge invariant if it depends explicitly on a specific SU2 matrix?
This is not the SU2 of the gauge. This is not the SU2 of the gauge. What I'm just saying is that you are rotating, this is a rotation on the parameter. It's extra solutions. This is not the SU2 of the gauge. I'm just saying that you can, you have any F written in this, you take a 2 by 2 matrix, multiply here, okay? And still this is Z2.
Oh, so it's a rotation of the sigma mn.
Yeah, just a rotation of the sigma. I have nothing to do with this. I say it's a new, it's a different solution. It's not an SU2 rotation, of course. F is bearing on the gauges. It's not gauge. I'm just saying that the most general solution is just this one with a rotation. This is quite remarkable. It's not obvious that this is the most general. But then there was a construction of my mathematician which they consider the most general. Okay, and this was. In the beginning, I don't know, even if it proved that this was unique. He finds a parameter solution And then he say, okay, I find this. And then mathematician extend to any k and find that this is the most general. Okay. I don't know. Maybe he has some argument why this was used at the time, but I don't know. Okay. Okay, but then we already arrived to the point. We already see what we learned a very important concept, that instant solutions are infinite. And they are parameterized by parameters, which is called the moduli space. Okay? And the moduli space, which I typically will, of k and n, depend on two integers. K is the instanton number, n is the rank of the group. For the moment, this is a 2 by 2. Okay? Therefore, what we learn is that k equal to 1 for SU2, the number of parameters are x0, n, which are positions. Okay? The position of the instanton. You see that, for example, if rho is small, imagine rho is very small. This x minus x0, when you are close to x0, then this f grow a lot. This is what is called an instanton. It's something that happens in an instant of time. At that instant of time, x0, there is a peak on f. This is why it comes the name of instant. Okay? It comes at some point in space-time, x. X is space-time, it's not space. It's different from a soliton. A soliton is something in space, instanton is something in space-time. Okay? Rho, you can imagine like the size of the instant. Okay? Rho is the size. Therefore, you have a position, 4 positions, 4 numbers that give the position of the instant. You have a rho, which is the size. And you have 3 SU2. In total, 8. Therefore, dimension of n, k equal to 1, 2 is 8. Okay.
So I'm confused now. So SU2 is the gauge group, right?
Yes.
So this is the gauge group rotation.
This is the matrix 2 by 2.
Right.
Yes.
So the SU2 rotation we are talking about, it's a gauge transformation.
Not, sorry. This is a matrix 2 by 2 that for leaf in SU2. But F is invariant on the SU2. F do not transform like this in SU2.
Why is it invariant? Sorry, I mean you take a trace in the action because F transforms it
right.
as a trace.
Fmn is not invariant.
F goes like U, F, U minus 1, right? So it looks exactly like that, doesn't it?
And for another bit of theory.
I mean, if the group is U1, of course, but this is SU2.
We are saying why this is not a gauge transformation. Okay, I don't know. Let me think about. For sure, this is the three solutions. The rotations for sure are. This is the counting. Now you are saying this is a rotate. This is true. This looks like a gauge symmetry. Then let me think about from where come these 3.
But it's a constant matrix anyway.
It's a constant. Yeah, it's a moduli. Okay. Now, let's do SUN. Now, the question is how, for the moment, let's do like that. For the moment, we know that there is 5 solutions. I already present you 5 solutions, okay? And my claim is that there are other 3 solutions, which are just rotations of 3 SU3 rotations. But this I should show you, okay? Okay, now let's go to SUN. Now, we already know an instanton of SU2. Then how you can do an SUN? Okay, you take the SUN matrix and put the instanton, I don't know, in some place, some SU2 inside the SUN. Okay? Now let's see how many parameters now we have. now I have the rotations, before were 3, now you can rotate all these big matrices. N squared minus 1. But any rotation you do here, any rotation you do in this block, will not change anything. If I put my connection here, any rotation you do will not change. Therefore, I choose subtract from this n minus 2 squared, which are rotation in this stuff. Therefore, how many parameters they have here? Have n squared minus 1 minus n squared plus 4n minus 4, which is 4n minus 5. Okay? Plus, these are just rotations. This is the analog graph. Therefore, for S1, for k equal to 1, S1, I have 4 positions plus 1 size plus 4n minus 5 rotations. Okay? Then the total dimension is 4n. Dimension of n1 n is 4.
Does it matter? Does it matter anyway the kind of embedding of SU2 inside if you pick another?
This is exactly counting that. What we are counting here are all possible embedding of the SU2 inside the SU.
So those matrices there aren't letting you.
This is the simplest one. I put in the first. What I could put here or put there. You see, if I rotate this n squared minus 1, is a rotation of this big matrix.
Yeah.
Therefore, with this rotation, you can bring this here or here. Or here. What I'm counting here is exactly this. How many times I can embed SU2 inside SU. And this gives 4n minus 5 ways. To this, I should add the position, and I should add the size. And this gives me 4n numbers. Therefore, we already, you see, already with this simple solution, we are able to write the most general k equal to 1 for SU. Of course, still, you know that it's the most general, but mathematicians prove that this is the most general. For it. What about k bigger than 1? Okay, you can imagine, okay, if instantons have positions, you can imagine that you can take k instanton very far away from each other. Therefore, the dimension of nkn, if I put the instanton very far away from other, the dimension should not change. I just put very far away from other, should be k times the 1 of n1. Therefore, it's 4k. Of course, it's more difficult to construct, but we already know that once we will construct the solutions for the general k and the general n, when we will send very far away to each other, they should look like this, with some different x0s. x01, x02, x03. Okay? Then what we will do now is to construct this model space, to construct explicit solutions with 4 kind n parameters describing this the general solution. And this is what is called ADHM construction. Any question?
So, if you want to construct these instanton solutions for SU1, you're still going to use these SU2 matrices.
Yes, for k equal to 1, I can just simply take this this stuff, put here in some place of SU2, and just rotate with either put here or here, any place where I put inside this big matrix is the solution of k.
And the fact that you're using SU2 is because you have a three sphere.
Exactly. Exactly. The simplest I can do is SU2. And the simplest is because the first non-trivial map to the 3 sphere comes from SU2. But any group that contains SU2, I can do this map. I can just take inside this big group, I take an SU2 inside. There are several SU2. I take any one, map to the sphere, k times, wrap k times this infinite sphere, and this is how I can do it. And then you have all the positions. The position of all these.
Francisco, this it holds for k bigger than 1, so the argument is it's going to be, no matter whether they are close together or far apart, it's going to be...
The dimension will not change, the solution will change.
Dimension will not change. But the dimension you're saying doesn't change because when they're far apart, for sure it's going to go as 4k over m, so that will not change even when it's...
Exactly.
That's the argument.
That's the argument. When they are far away, we know that they should be, already we know that we can construct 4km when they are far away. Now, when they start to move, I know that the solution should slightly change. And this is, but you see, any solution you find, I can always take the km and put very far away to show. Therefore, any solution should contain that one in some limit.
At the beginning you showed that if a connection is self-dual, then it is a minimum. And so it's an instanton, but it's not clear to me that any minimum is self-dual.
I show first that given k, what I show is that trace of f squared integral p for s is bigger than trace of f tilde, which was k times some parameters, some numbers, a p squared. You see that this is saying that fixing k, any configuration bigger than equal. Equal is false for this instant. Any connect, any fixed train, which is not an instant, will have an energy and is bigger than the instant one for the same k. What we say, k gives the topology of the solution. Then you have fixing the topology, you have infinite way of infinite number of configurations. Out of all these configurations, the minimum is the instant. Okay? When you do the Seiberg computation, what you should do is compute. You compute the minimum, and then all the excitations are. Let's say you fix k. That is any solution you find to the Euclidean equation of motion will contribute to that, but will contribute less than the instant because we have this Euclidean. Therefore, if you are in the classical one. In the classical limit, this will be the limit. I should say that I don't know any solution of this Euclidean equation which is not an instant. But this is my class. I don't know if they are the only solution. But for sure, I show you that they are the minimum for a fixed k. It could be also that they are the only ones.
Excuse me, let me ask you a question. I'm not understanding one detail when you consider SU2. So in SU2, these guys, the field strength lives in the adjoint representation, right? So each component should be a 3x3 matrix.
2x2. SU2. There are 3 matrices which are 2x2 matrices, which are the matrix SU2 by definition is a matrix 2x2, which is there are 3 of them.
The adjoint.
The adjoint is 3. Yes, but I always work in the fundamental representation. Yes, this is a good point. You can, when I say, you can work always in any representation. When I say trace here, I always say trace in the fundamental representation. The trace, the field is in the adjoint. In other words, the index here, A, you remember, I write A, F was F, A, T, A. This is a 2x2 matrix. And A is going from 1 to 3. This is my convention. Of course, you can do this in any representation, 5 times 5. Important is that the fixed trend is in the adjoint representation. Then typically, what most of the people use is to work in the fundamental representation. Typically, because quartz are always in fundamental representations, it's easier to do that. But you are right, you can work in any representation. But The important point is that this A goes from 1 to C, and this T you choose, and I choose just 1.
So then each component of the field strength is then a 2 by 2
2 by 2.
matrix. But when you go to the case of SUN,
Is N by N.
how do you modify the expression? Then
Because I say you have a matrix N by N where it's trivial everywhere, except in the first two, when it's given by this sigma matrix. Okay. Other questions? Please feel free completely to interrupt me, and I mean, it's very useful also for you. Where we was? Okay, we finished. Then we go to ADHM.
I think the second down as well.
No.
Right?
No.
Okay.
This looks like.
This part has been done by mathematicians, before you will see immediately. That is very abstract. But you will see that the elements, the ingredients are very simple. Therefore, just have some patience with indices and things like that. Well, the idea is, again, I look for the most general solution, and the idea is look again for solutions where Fn is proportional to sigma. So the main ingredient I will use is just that, again. Now, we will look for connections, An, which will be U bar, En, U. Where this U is a matrix. Let me put some index here. Where U is going from 1 to n. This is a matrix of SUN. Okay? And this lambda will go to 1 to n plus 2k. You see, if k is equal to 0, this would be just a pure gauge. Therefore, you can imagine this connection a sort of generalization of a pure gauge, because if k is not here, this is just a pure gauge. Now you put some k, some other numbers. You put some k. Then we will look for a connection like that. This is the main answer. And now the theorem is defined. Alien's construction say defined. If consider this matrix delta, which is a matrix n plus 2k times n, for delta is a matrix again, lambda u, which is made of this form. It's a constant matrix, A lambda u, plus a matrix that depends linearly in X. Okay? The statement is, you just consider a matrix that is linear in X. Okay? And such that delta u bar delta is equal to 0. Okay? So we're looking for a connection. Sorry, u is u bar u1, u bar times u is the element. Okay? Now the statement is that this connection, A n is equal to u bar en u, is a self-dual if this matrix delta satisfies this property. Let me write more specific here. Let me write this. Okay, what I'm doing here is you have this index lambda, which goes n plus 2k. I split it in two. U goes from 1 to n, and the 2k I write like I go from 1 to k, and alpha dot is from 1 to 2. Okay? You see, the main idea is that you find you look for a matrix that depends on x only through sigma, in such a way that when you do derivative of a and do commutator, you find sigma sigma bar, and this you get this this expression. Now we will see explicitly. But okay, the statement is that this, if you have delta, so define this. Okay, this connection is self-dual if delta satisfies an equation, which is delta bar. Delta is equal delta bar is a matrix U two K. Therefore, you have J I alpha dot lambda lambda J beta. Okay. Therefore, you see that the statement is that if delta satisfies this property, this proportional, the product of the two delta is proportional to the delta, f is an arbitrary function. Okay? If delta bar times delta is proportional to this, then this A is set. And this is what we will prove. Right, maybe let's write dot virgula to split. These are always rectangular matrices. Okay? The index 2k, lambda is an index that goes n and 2k. Maybe let's write everything in such a way that you keep in mind all the indices about how it's going. We have a matrix delta, which is lambda U. Sorry, no. No, this was U. This is 2k. Then we have a matrix U, which lambda U. Lambda is 1 to n plus 2k. And this n plus 2k we split like U alpha E. Then we have a matrix delta, which is lambda 2k. Lambda 2k. And this, lambda we call lambda E alpha dot. This E is going from 1 to k, and alpha dot A alpha. What else we have? That's all. And then we have these properties. U bar U is equal to 1. Delta U bar C bar delta, delta bar U. Delta U bar is equal to delta U bar is U bar delta is equal to zero. Where F is, let's write also here, F is the matrix I is of so these are the ingredients of the ADHM concept. Okay? You keep in mind that this, what the computation that we do today, you do once in your life. The importance is that you know how to solve instanton solution. All these matrices, this is just a way to construct explicitly the solution. Okay, then don't worry about that. Of course, it's a very technical derivation, but it's very simple. You see, once you introduce this rectangular matrix, now we will see how easy you see that this is set.
Francisco, can you just read those indices? Can you just read them out?
Ah, yes. Okay, I have the main objects are u lambda small u, where lambda goes from 1 to n plus 2k, and this n plus 2k sometimes I will split in n, which is u, and I alpha, which is the 2k. I goes from 1 to k, and alpha dot is 1 to 2. Delta is a matrix lambda, is a matrix n plus 2k times 2k, and it's lambda I alpha dot. Okay, I write explicit names because then you immediately remember how big they are. These matrices. Okay, then u bar u is 1. Delta u is roughly u is the kernel of delta. You have a rectangular matrix and then you just multiply another matrix. Then it's delta u bar is equal to 0 and also u bar delta is equal to 0. Sorry. Yes, you see, already from the index, you see that this makes no sense. Because you need to multiply these two, you need that the lambda is here. Therefore, it should be delta bar u or u bar delta. Okay? But you see, delta bar f, you see, delta bar is I alpha dot lambda j delta dot, and this is f minus 1 I j delta alpha dot. Okay.
So bar is just a transposition.
Bar is a Hermitian conjugate. I said, yes. The bar, every time I write a bar, is Hermitian conjugate. You complexify and
The indices in the first line of the j alpha dot, or
sorry?
the first line, yeah, the left hand side. Yeah, there.
So, yeah, it's like
Lambda 2k. 2k is j alpha.
Okay.
Yeah. Ah, sorry, I get that. J alpha dot. And this is lambda j. Okay. Okay. Now it's very simple. We have this matrix. We should compute the fixed state. Okay. Let's compute the fixed state. Fmn was defined as Bn An antisymmetric plus Am AM antisymmetric. Sorry, this index, by this index, I mean I am antisymmetric, I mean 1/2. Okay, the antisymmetric part of a disk. Okay, then let's compute. This is 2 times derivative of, this is dn, of u bar dn u. Now you see, since this is antisymmetric, I cannot act here, because I will have dn antisymmetric, and this is 0. So for this act only here. Now let's compute this. This is 2. This is u bar dn u bar dn. Okay. Now let's observe the following scene. Let's observe that we say that u bar u is 0. What about u bar? U bar is not 1, but this is 2. Let's see. You see, if I multiply here by u, my claim is that this follows from this claim. If this is the 1, this means that if I multiply here by u, see this term cancels because you have delta bar u is equal to 0. U bar times u is 1, therefore this is just u. Therefore this 1 is u, is u. If I multiply by u bar here, the same thing. U bar times u is u bar. This means that this quantity here is dead. Okay? Therefore, you see, this matrix u bar u is a matrix in UN. Typically, you have this is a matrix that u bar u is identity, but u bar is not identity. Use supplement by this and this. It's another way of writing it. And this will be very important because what will happen, you see, I don't know what is the derivative of u bar. But I know what is the derivative of delta. Okay? The derivative of delta is just a constant. This is just a constant.